Hey, this is just an addendum to our discussion on Conic section applications, looking at Conics Packet 2, still on the problems on page 12. And I know we had already spoken or we had worked through most of problem 4, but I still think these problems are some of the trickiest Conic applications to think about. And I wanted to make sure we finish this one too. When we last left, we had an equation to model where this lightning bolt might be, but we didn't actually answer the question. And there's part of this picture I want to slightly alter. I just put the lightning bolt up in quadrant 1 at any point along the hyperbola, when really I should make sure, whoops, do that later, ignore. I should make sure that I put it exactly due north of point A. After all, the problem does say that the lightning was known to occur due north of the person who is standing at point A. So to be a little bit more accurate about it and to help solve this question, I'll just put a dot directly due north of A, meaning we know one of its coordinates. We know that that lightning strike occurred at the x coordinate 2640. 2640. And the y coordinate we don't know. We want to know how far away from A was that lightning strike. So we can always go back to the function that we wrote as our model in the last session and just plug in a 2640 for x. So it'd be 2640 squared over 550 squared minus y squared over 6667100 equals 1. And then it's going to be up to you to solve this algebraically. I recommend moving the fraction to the other side, so subtracting this fraction over, and then multiplying through to get what y is. And when all's said and done, you can still say, check your answer with this is accurate, that the lightning strike occurred 12,122 feet due north of the person standing at point A. I was thinking what could be better than doing one of these than doing two of these just to get used to them. And I think the second one, does it have to do with sound and not light? Or the first one was sound. This is more the speed of light. And we're going to use this approximation. 186,000 miles per second is how fast light is going to travel. And notice that the diagram's given, thank goodness, in this one, but it's the same setup. You've got info about two foci at A and B, capital A, capital B. You have a long distance radio navigation for aircraft and ships, and sends pulses traveling at the speed of light. The difference in the times of arrival at these pulses at an aircraft or ship is constant on a hyperbola, right? That's how you construct a hyperbola. Keep the difference in the distances from two foci constant. Assume the two stations are 300 miles apart. We'll use that. And have the coordinates. Okay, that's perfect. We've got A is going to be, C is going to be 150, right? If A is where the focus is. So from here to here is 150. Let's write down that center to focus is 150, in hopes of constructing an equation of this hyperbola as a model. Find the x-coordinate of the position of the ship when the time difference between the pulses is 1,000 microseconds. So that should mean 0.001 of a second. We're going to use that too. So if it took 0.001 of a second for the point A and point B to see the pulses, we'll say that was enough time to have traveled 186 miles. So 186,000, that speed of light, miles per second, times just 0.001 seconds, just gives you 186, and we'll say miles. And that distance, like in the last one, it is going to be 2A. My best explanation for that is to think about the picture with this ship that's on the hyperbola to be transferred down to where the vertex is, right? The difference between these two dotted distances is supposed to be a constant 186. And think about it. If this slid down here, the difference between this whole distance from B to that vertex and this distance here is that 186. And this long thing minus that little chunk leaves you with just the distance between the two vertices. It just leaves you with 2A there. Same thing happened in the last one. And this can get us A. We'll say underneath, we can just call A 93 if 2A is equal to 186. So this is enough to get the equation of a hyperbola, right? We know we use normal Pythagorean theorem. 150 squared equals 93 squared plus B squared to get B. Solve for B squared. Go ahead and try that. And you get B squared is 13,851. That can be used in the model. And now let's write the equation so we can answer the question that's presented in part A. So we're centered right on the origin, and this is a horizontally oriented hyperbola. X squared over a squared, so 93 squared, minus y squared over b squared, which we just got, 13,851 equals 1. And find the x-coordinate of the position. Well, we've got these coordinates x comma 75. We have enough to do a plug-in like the last step of the last question, whereas 75 goes in for y. We're trying to find x. So x squared over 93 squared minus 75 squared over 13851 equals 1. And you got to do the algebra here. You got to add the fraction over, multiply through by 93 squared, and square root the result. So you get x is roughly 110.3 miles. And that would be the y, or yeah, that would be the x, x coordinate of the position of the ship. B and C, let's take a look. Some different questions here. Determine the distance between the port and station A. Well, here's the port, and here's station A. It looks like all they want is that little distance from, we could say, vertex to focus. So we know A and C should get us this. C is this whole distance here, 150 units. And A is this little distance here, 93. Not really a little distance, but C minus A should do the trick here, should give you the distance from the port to the station. So a quick subtraction, 150 was C minus 93, which was A, that many miles. So 57 miles apart. And I like the last question. It says, find a linear equation. Now think, what was one question you used to have to answer about hyperbolas where you needed a linear equation? Well, we need the approximation of the ship's path as it travels really, really far away from the shore. Think of a nice, cool dotted line that we have that's an approximation that the hyperbola kind of hugs because it's an approximation for where it's going to go as x gets bigger and bigger and bigger. And if you're thinking asymptote, your head is in the right place. This asymptote equation, especially as x gets bigger and bigger and bigger, should approximate the ship's path. So I'll remind myself here that we just want an asymptote equation. And I'll use the equation with a positive slope that runs up through quadrant 1 and further because it looks like that's the direction that particular ship is going in. Well, we can use point slope form. It's been a while. So we know the asymptotes both go through the origin, the center of this picture. So y minus 0 equals, technically it's plus or minus, but when all said and done, I'm just going to keep the positive. We'll get a slope and then it'll be x minus 0. So here's a case where it's horizontal. We need b over a. You're rising b and you're running a to get to another point on this asymptote. So we will keep b, which is the square root of 13851, divided by a, which was 93. So this can be cleaned up, right? Y equals, let's just use the positive, square root of 13851 over 93, x. And then I thought to myself, how cool do I want to be? How thorough do I want to be? How much of an overachiever do I want to be here? We could honestly just write that as a decimal, that slope. I'm sure it would be fine. But could we go above and beyond and try to find the exact simplification of that fraction? Do you want to? Are you saying yes? Well, it's kind of fun. It can unleash the inner simplifying radical lover inside of you. Here is a 13851. And I learned this trick that if you add up, you know the trick about 3 being divisible by the number? Like if you add up the digits and 3 goes into those digits, it's probably divisible. It's definitely divisible by 3. So 13851 divided by 3 happens to be 4617. And if I divide that by 3 again, because 4 plus 6 plus 1 plus 7 is also divisible by 3, I get 1539. Turns out, as luck would have it, a bunch of 9s go into this big number. So your first split up is 9, and I wrote this down, 9 and, well, we just got 1539. 9 also goes into 1539, so it's 9 and 171. And would you know it, 9 also goes into 171, so it's 9 and 19. So the square root of 9 3 times sneaks out. You get a 27 on the outside. So simplified, y equals 27 square root of 19 over 93 times x. Pretty good, pretty thorough. All right, I will see you next time.